So how do we manage this? Again, here we've got the same plot from before, showing an inrush current in blue. It's a current that spikes sometime after we turn the switch on and eventually returns back to steady state. In this case, we've remodeled the circuit on the left to show some resistance in series with our generator to replicate a more realistic circuit. And so if we look at the voltage across our load, we can see that the moment we turn that circuit on, because of that inrush current, we see a big drop in the voltage that our load is providing. Of course, this generator is common to all of the appliances in our household, and so that voltage drop will be seen by anything else that's connected to the grid. And this creates a problem for all of our downstream components. If we can soften the rate at which the switch turns on so that it turns on more slowly, we can reduce that dV by dt happening across the capacitor and then reduce the magnitude of the current spike, which in turn reduces the voltage sag on our grid. This technique is known as slew rate control or soft starting. And effectively what we do is we control the rate at which a circuit is switched into use. In a domestic load, however, slew rate control is often a little bit of an overkill, and so we might use something like a fuse. Here we've got a slightly different circuit. We've got a resistor that represents the real power that's consumed by a circuit in parallel with some capacitor that represents this reactive component. And of course that capacitor is responsible for this inrush current or the surge factor associated with that circuit. In this case, the moment we turn the circuit on, we see this current shown in blue ramp up to the surge current and then reduce back to our steady state current. Now this could be a problem for the fuse because if our fuse, for example, is present to detect a fault and the fault level is set up here, everything will behave as expected. But if our fault level was set a little bit lower, you can see that the fuse will indeed be tripped by that inrush current despite the fact that the steady state load lies below the fuse rating. In practice, we can mitigate this by using sophisticated timing circuits or RCDs where we ignore this inrush current for some period of time, delta t, and that time will be tuned such that we expect the circuit to be in steady state by the time the fuse needs to trip. So if a fault is present for this block of time shown in grey, we'll ignore any current that exceeds our maximum rating, and then we can trip the fuse just after.